want to pick up where we left off last time. So I apologize. How many people, like, just give me a thumbs up if you saw the video that I posted with the e-ticket help? Yes, okay. I apologize that it didn't have audio. I don't know why. I redid it with audio, so that's available. Let's just go through one quick example, and maybe this will be helpful. Give me a 1 to 5 on that assignment. 5 meaning got her handled, piece of cake. 1 meaning I'm having some issues. Somewhere in between. Okay. Okay. Let's take a quick look at an example that might be helpful. So, whoops, not that one. There we go. Is it something like... Oh, I know what it is. Here it is. One like this. Something like that, right?
I don't think you're straight.
Oops. Is that better? Okay, there we go. Okay, so something like this, where we're given some function, and they're asking us two things. They want us to use technology to evaluate the limit, right? Which when we're evaluating limits using numerically or graphically, to me that implies with technology. I mean, you could sit there and make a table and plug values in, and that's fine. I mean, we talked about that yesterday, how you could accomplish that. But let's get real here, and let's talk about how we would use technology to do this in the best possible way. So let's pull up Desmos. I got to find it. I got about a jillion tabs open. Oh, there we go. Okay, hang on. Okay. And what do we got here? So I'm going to change this slightly. So we have 1 plus x plus 10 minus 1/6 divided by x plus 4. And we're trying to evaluate this limit as x approaches -4. Okay, before we even jump into this one, though, when we're taking something like the limit of f of x as x approaches -4, think about this in terms of our ant analogy. As dorky as that sounds, it's very useful. So if we've got this little two-dimensional ant, point-sized two-dimensional ant, crawling along this function, the graph of this function, which of course is two-dimensional. Something I failed to mention the other day about these calculus ants, they're fairly highly evolved. They have developed the sense of two-dimensional position. So they're able to just sense their coordinates as they crawl along these functions, right? They inherently just know the x and y value every point that they're on. Fascinating little creatures. As an ant crawls along the function approaching an x value of -4, is the limit interested in where he ends up when he steps on -4? Is that a correct way to think about a limit? Somebody correct me if it's not. Caleb, I saw you shaking your head. Help me out here. What's going on? Yeah. Okay, good. It's the limit is actually does not involve where he actually ends up. It only involves the concept of where he anticipates stepping as he gets arbitrarily close to that point. As far as the limit is concerned, and I can't emphasize this enough, as far as the limit is concerned, he never gets there. Okay, it's just where does he think he's going to be, right? So let's look at this in terms of the graph then. When we look at the graph, we're interested in the behavior of the graph at x equals 4, right? So if I plug in something like, if I plug in, or negative 4, sorry, if I plug in negative 4, well, the function isn't even defined there. So I can't get an answer. I can't evaluate this function to get my answer. What do I have to do instead? Get close to it. Now, in this case, if I zoom in on 4, it's probably not going to help me very much because I can't really tell what that value is, right? So what I'm going to do instead is I'm just going to evaluate the function very, very close to 4. So let's try something like 4.1. Well, there it gives me an answer. Is that close enough? I'm just trying to get an answer. If you look at the directions here, they're obscured a little bit, but I believe they say rounded to 2 decimal places, right? So we only have to get this thing accurate to 2 decimal places. It doesn't have to be perfect. So I'm just going to continue to get closer and closer and closer to that x value until out to 2 decimal places things aren't changing. Well, I'm already there, aren't I? Rounded to 2 decimal places, what's the y value that the ant thinks he's going to step on? Negative 0.3, right? Point 0.03. I see what you meant, yeah. Negative 0.03, exactly. But we want to make sure that it's not just from the left that that's happening, right? The limit, there's an implied symmetry here, isn't there, with a limit. We want to know what's the answer going to be when the ant approaches negative 4 from either direction, right? And there's a kind of a bigger concept that this is like a graduate level concept at least, but you can start to think about it now. A lot of times in physics, really sophisticated proofs you can accomplish by appealing to the isotropy of space, right? Which is really a cool way to do it. All that means is in space, there is no preferred direction, right? It doesn't matter which direction you approach something from. As far as space is concerned, you should get the same answer, right? That applies to all different dimensionalities of space, 2 dimensions too, right? There is no preferred direction in our little 2-dimensional world where this calculus ant lives. The space should be isotropic. He should be able to approach negative 4 from either direction and get the same answer, right? The gods of Flatland, they don't prefer from left to right or right to left. The math gods, they don't care. Neither one is preferred, right? So we should be able to approach from either direction. So then I want to approach negative 4 from the other direction as well. So that would be something like, what, negative 3.9? But I want to get close. Whoops, I got 2 negatives there. I want to get closer than that. So if I just keep adding 9s, I'm getting closer and closer and closer to negative 4 from the right side this time instead of approaching from negative values from the left. Well, what do you notice? Same answer, right? So that is my limit. And we can see from the graph, that's not unexpected, is it? Because I want to approach negative 4, not 4. What am I doing? I got to go on the other side. But we'll see it still works. If I go to the negative side over here and I focus in on negative 4, well, we can see from the graph that an ant approaching from the left or approaching from the right, they're approaching the same value, aren't they? Right? We can see it graphically. We just demonstrated it numerically. So the first part of our answer is negative 0.03. Okay, questions? Does that make sense? So there's kind of a quick numerical approach to this, and that's one way that we can effectively take limits. It's fine. That works, right? Okay, what about the next part, though? They want the domain. Now, we got to go back and think about, I'm sure you talked about this last year. We spent a lot of time on this in Algebra 2 a couple years ago. So we want the domain of values, all the values of x, the set of values that are legal, that we could plug into this function that wouldn't violate our two rules of dividing by 0 or taking an even root of a negative number. Well, there's no even roots here, but I do have variables in denominators, don't I? Right? So if let me go back to here for a second. There we go. So here's a fraction involving an x in the denominator. Right away, what value of x can we see that we have to exclude from the domain? Negative 10. Good. Here's another one. Whoops. There's a denominator. So what other one do we have to eliminate? Negative 4. Okay. So there's two ways we could do this. And unfortunately, this crappy new Canvas version doesn't do a very good job. It kind of mangles up Moodle as we know and love it. But a couple ways we could say that domain. A lot of people, I think, initially said, okay, I'm gonna write this out as all the values that we could use, and that's fine. So negative 10 and negative 4 were our excluded values. So then we should have been able to say something like x is less than negative 10, or, right, that'd be an or statement. Oh, darn it. Or x is greater than negative 10 and less than negative 4, or x is greater than negative 4. Everybody see that the only values I skipped over were negative 10 and negative 4, right? Okay, it doesn't like that. I don't know why. That used to work, but just somehow in Canvas it doesn't. But that's okay, because there's a better way to do this anyway. And this is a good thing to learn. Notice the hint here. If discrete values of x are excluded from the domain, well, what's discrete mean? Yeah, single or specific, right? So if there are individual or specific values of x that are excluded from the domain, the easiest way to say the domain is not all the complicated values that work, but just the few values that don't work, using the not equal to sign. So a better way to do this would just be to say, okay, we know the values we have to exclude. X cannot equal negative 10, and the other value is x cannot equal negative 4. Now, what kind of conjunction do I have to put in between there? Is that going to be an and or an or statement? It's got to be an and, doesn't it? Because those two things have to be true at the same time. It can't be negative 10 and it can't be negative 4. So we would just put an and statement in between, and that works. Okay? Make sense? Okay. All right. So moving on then. I'll skip over this. We just did an example that takes care of that. So let's kind of go back to the definition of a limit here again real quick. I just make sure I take just a second and make sure we understand this. Here are the important parts of this, right? So the way that we say this statement in calculus, this is said as literally the limit of f of x as x approaches a is L. That's how we say it, right? What's that mean? Well, another way of thinking about that would be to say something like, as x gets closer to a, f of x has to get closer and stay closer to L. Okay? So when we're talking about a limit is only going to apply to functions where that is true. We're going to end up today, hopefully we'll get this far, talking about some cases where limits don't work. They don't work when that logic doesn't apply. A limit only works when the closer I get to a certain x value, the closer I get to an individual limit, right? If I get arbitrarily close to an x value, I can get arbitrarily close to a single y value, which becomes the limit. Now, it's not going to work if, as I get closer to, if I'm taking a limit as x approaches 4, for example, as the ant walks closer to 4, the limit is only going to work if the y value keeps converging on a specific value. If the function does something crazy, like as the ant gets even closer to 4, all of a sudden the limit starts to change, the value of the function starts to change in a way that's not predicted, right? It's no longer converging on a value, then that function is not one where we can take a limit, and that sometimes happens. Okay, we'll spend a little more time talking about that soon. And so here's where I think we left off. Here's the concept of a limit. As x approaches 1, here's a function where it works. Notice that the y values continuously converge on a value, and in this case it's 3. As I keep getting closer and closer, the y values are going to converge, whether I'm walking from the left or the right. They're going to converge on that y value. So in this case, the limit is 1. Okay? We would say the limit of f of x as x approaches 1 is 3. Just brief review. I mean, like if we could do this, we could do this graphically also. In this case, as x approaches 1, we can see on the graph that we're approaching the point 1, 3 with coordinates 1, 3. The ant never gets there, but his built-in position sensor tells him, okay, I know where I'm going to step. I'm going to step on the point 1, 3 when I get there. He never gets there, but he anticipates that. Okay, I think we can skip through that. Just using tables, we get the idea. We used Desmos today. Okay, let me show you briefly. I hope I still have this thing. If I don't have it now, I'll show you tomorrow. Yeah, they took it away. So I'll show you tomorrow how you can do this on your TI-84 numerically. But for now, just use Desmos. Okay, what about this one? So we've got some function graphed here, g of x. I want you to tell me, and don't say it out loud, I want everybody to think about this a little bit. I want to know, what is the limit of g of x as x approaches -1? Think about that. Okay, now before you tell me that answer, and I'll write that up here too, we're going to fill in both of these blanks. First of all, can somebody tell me what is the value of the function g at -1? G of -1 is what? 4. 1, 2, 3, 4. Because this point right here has coordinates 1, 4. So when an ant actually steps on an x value of 1, he ends up at the point 1, 4. Okay? What's the answer to the red limit? The limit of g of x as x approaches -1 is what? 3. Okay, let's vote on that. Give me a thumbs up if you agree, thumbs down if you disagree. Okay, I'm seeing mostly thumbs up. Caleb, you want to defend your answer there? I just saw a thumbs down. Okay, that makes sense. Somebody who had a thumbs up there? Who had a thumbs up? House, did you have a thumbs up? Okay, tell me why. We got a fierce debate going on here. Okay, you cut out a little bit. You got bad audio there. Somebody else. Okay, I'll tell you what, the answer is 3. Somebody tell me why. Right. Okay, good. Good. And think about it this way. Now, so this ant, they've got this built-in ability to sense their location. Well, a two-dimensional calculus fog, maybe it's calculus smoke rolls in. They got a bunch of fires in flatland here, and the two-dimensional smoke is rolling in, and this ant, and they're red ants, and this ant is walking along. That's a blue ant. This red ant is walking along from the left, and his buddy's walking along from the right. They can't see where they're going. The smoke is so thick. But as they get closer and closer to their x value is approaching -1, they can't see where they're going, but where do they anticipate stepping? Because in the limit, that's what that arrow means. We're approaching -1. We never get there, right? And so we're only concerned about the place that they anticipate stepping, which has coordinates 1, -3. Or sorry, 1, +3. And so the answer is 3. Because we never get there, right? That's the thing about a limit that's a little bit counterintuitive. You never actually get there. It's just the point that you're approaching, okay? So the value of the function in this case is different than the value of the limit. Okay, let's look at some of these graphs now. Oops. Actually, I'm going to come back to that. Okay. We're going to up the ante here a little bit. We're going to improve our definition of a limit. Okay, and to do this, to be a little bit, it gives us some more power to talk about functions, and it gives us an improved definition of a limit. If we start to think about, instead of just a general limit, we're going to think more specifically about one-sided limits. We're going to talk about limits as the ant is approaching specifically from the left or from the right, okay? So we're going to say something like, now more descriptive, we're going to say the limit of f of x as x approaches a. What do you think that negative sign right there means? It assigns a specific direction to where the ant is coming from. Okay, right. So it could mean either thing. Think of it this way: it's approaching from -infinity, from the direction of -infinity. So it's approaching from values that are less than a, right? So this means we're approaching from the left. Okay, we're approaching from the left, from values of a, starting at -infinity and approaching a. So the limit of f of x as x approaches a from the left is L. That defines a one-sided limit from the left. From the right, the only thing we have to do is we just have to change the direction where the ant is coming from. This is how we would define a limit from the right. The limit of f of x as x approaches a from the right, which we indicate as a plus, from the direction of positive infinity, is equal to L. Okay? If those two things are true, then we can say that the two-sided limit is L, because both the ants approaching from the left and the right agreed on an answer, and that was L, right? Whether you approach from the left or the right, we got the same answer, and so therefore we can say, in general, the limit of f of x as x approaches a from any direction is L. Okay? That's our improved definition of a limit where, we're involving the two one-sided limits. Okay? Something I'll remind you about from your geometry classes a couple of years ago, and I'm sure I mentioned this in Algebra 2. Whenever you see the statement if and only if, which is sometimes we abbreviate as IFF, that implies that this is a relationship that works in both directions. So we could say that the limit of f of x as x approaches a is L if the limit of f of x as x approaches from the left is L and the limit of f of x as x approaches a from the right is L. Or we could reverse that, and we could start this side and say the one-sided limit from the left is L and the one-sided limit from the right is L if the limit of f of x as x approaches a is L in general. Okay, it works both directions when you see if and only if. You can turn it around either way, and we get a conditional statement starting with either end of that. Okay? Just a quick reminder. So let's define these in terms of two-sided, a two-sided limit in terms of two one-sided limits. Oh, I said that backwards. It's supposed to be two one-sided limits. Okay. So in this case, we did this one last time we met, right? We looked at this graph, and we could see from the graph that the point the ant was approaching was the point 2, 4, right? Well, then that just means as x approaches 2 from the left, the limit is 4, and as x approaches 2 from the right, the limit is also 4. Both of the one-sided limits agree, and so the two-sided limit exists, and it's the answer that we predicted. Okay, what about this one? What about this one? So you tell me here on this function, what's the limit? And this is g of x, right? That's how this is defined. The absolute value of x minus 2 divided by x minus 2. The limit of g of x as x approaches 2. How do I say from the left? Good. 2 minus with a superscript of minus. Okay. Equals, well, I want that answer. I want the limit of g of x as x approaches 2 from the right. And then I want you to combine that information to tell me what's the two-sided limit of g of x as x approaches 2. So what about the blue one? Everybody agree? As an ant walks along, and this is a blue ant, I guess, as he's walking along this function. Yeah, okay, it is, right. So there's positive 1 and there's negative 1. As the ant approaches x equals negative or positive 2, from the left, he anticipates stepping on that point, doesn't he? The coordinates of that point are 2, negative 1. And so the limit from the left is negative 1, right? Give me a thumbs up or thumbs down on that. Okay? What about this statement here? The purple ant is approaching from the right as he walks backwards towards x equals 2. He anticipates stepping on the point 2, 1. So the limit from the right is positive 1. Well, what does that tell you about the two-sided limit? Does not exist. Yeah, there is no limit. There are separate one-sided limits, but there is no limit. When I say just plain old limit, I'm applying a two-sided limit, right? So that's one that does not exist. Okay? How about something like this? So I want to know, once again, I want to know the limit. This is an x value of 2. The limit of h of x as x approaches 2 from the left. I want to know the limit of h of x as x approaches 2 from the right. And then we'll combine that to say, what's the limit of h of x as x approaches 2? Okay, what about the blue one? As this ant approaches 2 from the left, what's the limit? Okay, the curves keep going upward. That's what we call an asymptote, right? Right, so there's a vertical asymptote here where the function is running into this brick wall. So it's just got to keep going up. And so people said infinity. That's a good answer. That's a really good answer. Okay, I'll take that answer. Same thing from the approaching from the left. Everybody agree? Everybody agree? Infinity? And so they seem to agree, don't they? The two, it doesn't matter which side we approach from, the answer is infinity. Okay? So does the limit exist? Seems like it. I got the same answer. Okay, so if it exists, it makes sense. If it exists, we should be able to write down the point the ant anticipates stepping on. Uh-oh. That's a problem, isn't it? Yeah, the closer the ant gets to 2, the higher he goes. It just accelerates. The slope is constantly steepening. And so he can't ever point to an individual value that he thinks he's going to step on, right? So this is another example where the limit doesn't exist. And it doesn't exist. Neither of the one-sided limits exists, nor does the two-sided limit exist. Now, saying infinity might be useful because it's telling us the direction the ant's moving in, but this is still an example where the limit doesn't exist. Right? Infinity is not an answer. When we want to answer to a limit, we want a specific number, don't we? If we go back and think about all of our discussion so far, the entirety of our discussion about limits, the idea is we want to be able to get a number for an answer, the value the ant anticipates stepping on, and we can't do that here. So even though these are excellent answers and they are descriptive, this is another example where a limit doesn't exist. Okay? Let's do a little practice. Let's try something like this here. So use the graph of G in the figure. So here's our graph of G to find the following values if they exist. If a limit does not exist, tell me why. So let's just go through this. And I want a different answer. So a different person has to answer each part of this. You can volunteer on your own, but don't be afraid to be wrong. It's okay. So first of all, what is G of 1? Think about that one a little bit. Maybe just type it in the chat. That'd be a good way to do it. Just type it in the chat so I can see how we're doing. What is G of 1? So far, so good. Does that make sense? Good. 4 is the answer. Okay, see lots of right answers. And why is that the answer? Because the ant actually can stand on that point, right? That's part of the function, and the coordinates of that point are 1, 4. So G of 1 is actually 4. Good. What's the limit of G of x as x approaches 1 from the left? Okay. Type it in chat. Good. I'm seeing the right answer. 2. Because the ant anticipates stepping there, and so that's the limit. That's where he thinks he's going to step. What's the limit of G of x as x approaches 1 from the right? Type it in. Okay, I'm seeing lots of 4s. That's good. Because in this case, he anticipates stepping there. Does it matter that he actually steps there? No, doesn't matter. That's where he thinks he's going to step, though, when he walks from the right. What's the limit of, therefore, what's the limit of G of x as x approaches 1? Good. Doesn't exist, does it? Because the one-sided limits from the left and the right don't agree. So that's DNE. Does not exist. What's G of 3? Okay, good. Lots of 1s. Perfect. There's a solid endpoint, so we know that's where the function is actually defined. So G of 3 is 1. What's the limit of G of x as x approaches 3 from the left? Okay. Good. 4. The ant's walking towards that point. He anticipates stepping there, doesn't he, on a y value of 4. What's the limit of G of x as x approaches 3 from the right? Good. He anticipates stepping there. Okay. What's g of 4? Good. 2, because he anticipates in this case stepping right there, doesn't he? And because he does step there. There's the point. What's the limit of g of x as x approaches 4? Yeah, 2, because he also anticipates stepping there. In this case, he anticipates stepping where he actually does step. Okay, but the two are different things. So let me just reiterate here. These are really all we've really talked about so far are numerical approaches using tables or Desmos, right? And graphical approaches using graphs, probably Desmos. We haven't yet gotten to the analytic stuff. We'll get there. Okay, so let's move on and let's define the kinds of behaviors. There's 3 special kinds of places where limits fail to exist, and we've already talked about 2 of them. One of them was, we dealt with this a little bit ago, right? Where there's a gap. When there's a gap in the function, we get different limits from the left and the right, and so the limit doesn't exist there. Okay, there's one type. Here's another type. Unbounded behavior, like we just saw. So if there's an asymptote, right, there's an infinite behavior in a function, then the limit doesn't exist either. Okay? We'll discuss all this stuff in more detail when we get to infinite limits, but you guys are so smart. Already you even get that we could say infinity there, and that's useful, but it still is not a limit. Third kind is weird. Okay, I want to do this. How much time we got? Because I really want to do this with you. 11:40. Okay, I think we got time. 11 minutes. So we'll do our best. So let's look at a sine function here for a second. Let's look at, and I'm going to pull up. I made a little Desmos form yesterday, so let me pull that up. Let's see. There it is. Okay, and I think I even linked. Oh yeah, okay, I linked to it here. Never mind. I'll link to this on the notes, so you guys can go to this too if you want to mess around with it. So y equals sine theta. Okay, so think about what this means. This is just functional behavior. Think about a function like a machine, right? We're going to feed the machine values of theta, and it's going to output numbers based on its rule. Well, in this case, it's just a sine function, right? If I feed a value of theta that's equal to pi fourths, then it's just going to calculate the sine of pi fourths for me, okay? So we could replace those with x's if we wanted to. No big deal, right? If I want to graph y equals sine x, that's easy to do. Here I've got y equals sine of a times x. Well, wouldn't that be the same thing? If I let a equal 1, that's the same thing as y equals sine x. There it is, right? Big surprise. It's the same thing as y equals sine theta. Okay? Okay, but what happens here if we want to change something inside the function? If I'm going to substitute for that theta, I'm going to substitute a 2x, right? And I want to know what this function now is of x. The function doesn't care how it's being fed values. It's being fed input numbers, and it's going to calculate output. Oh, you guys can't see that. Whoops, hang on. Gosh, that was kind of dumb. Let me go back a step, right? Here's this fancy Desmos tool I created yesterday, right? So there's y equals sine theta. Big deal. We all know what a sine function looks like. If I'm going to let y equal sine of a times x, well, if I let a equal 1, that's the same thing as sine x. So that graph sits exactly, the red graph sits on top of the blue graph, okay? But what if we want to change this a little bit? What if we want to multiply the x by 2? What does that do? Remember that the function g of x, the sine function, doesn't care where it gets the input values. It just gets input values. So in this case, if I input a value of pi fourths, and what is the value of sine of pi fourths? Type it in your chat window there. Like if I made this, for example, f of theta instead of y, I could go down here and I could say f of pi fourths, and there's a decimal representation. What's it telling me? What is that actually? What's an exact answer to that? Oh man. The trig brain cells kind of atrophied over the summer, it looks like. So sine of pi fourths is just square root of 2 over 2, right? So that's the output. And if I were to kind of focus in on this and I were to go over to pi fourths, I would find that I'm at a point square root of 2 over 2. Okay? But let's look at this red function, or the green function up here. Sorry. What if I'm taking the sine of 2x? Then the input value, if it's still pi fourths, right? The x value that I'm inputting is pi fourths. What's the angle that the sine function is actually being fed now? Right? I'm multiplying 2 times the input value. So somebody turn on your mic and just tell me real quick. Pi over 2. Yeah, 2 times pi fourths is pi over 2. Well, hold it now. What's the value of a sine function at pi over 2? At pi over 2, the value is 1, right? So instead of now being, if I just had a regular f of x equals sine x, instead of being at the point pi fourths f of pi fourths right, which is right there on the blue function. Down here on this green function, where am I going to be? On the green function, I'm going to call this g of x, let's say. G of x equals sine of a times x. Okay? And I want to go down here. I'm going to do g of pi fourths. Oops. That's not pi. G of pi fourths. Okay. And let's even just do the point. Let's make it a point instead. Pi fourths, g of pi fourths. Need a comma. Forgot my comma. There it is, right? I want to make that red so it matches our red curve. Okay, there's that same place. Okay, but if I turn the a into a 2, what's that going to accomplish? Now that the function is seeing the input number 2 times pi fourths, which is pi halves, right? It's going to see the point on the blue graph that would have been at pi, oh my gosh, can't type, pi halves, f of pi halves, there it is, right? It's going to see that point when we input a pi fourths. Everybody see that? So if I make the a, let's turn this one on. If I make the a into a 2, look what it did to the function. It compressed it. Everybody see that? Why that happens? Because now it's seeing the sine function. When I input a pi fourths, the sine is already seeing pi halves. Right? The input number for the sine function when x is pi fourths becomes pi halves. And so the effect of this, you might remember this from trig last year, right? The effect of multiplying the input variable x by a number bigger than 1 is I'm going to compress that function, right? The bigger a gets, the more compressed it gets. If a is equal to 3, I get through a complete sine graph, a complete cycle of sine function 3 times faster than I would have if it was just a plain old sine graph. Agreed? Everybody with me? Okay. So then, if I make this thing, like, let me make A really big. Like, what if A were 20? I mean, look, I've compressed that thing a bunch. Okay? All right, let's go a little bit further with this. What if we're going to now do something like sine of x squared? Okay, well, think about what's going to happen here. See if you can anticipate what this is going to look like. If I make a new function, what's the wrong one? Is it that one? No, it's that one. There we go. If I make a new function that's the sine of x to the b, well, if b is equal to 1, it just looks like a regular sine function. But what if I made that b into a squared? What's going to happen? What's going to happen to the angles that the sine function is seeing as x gets bigger? Think about what happens to x squared as x moves from 2 up to 5, right? When x is 2, 2 squared is 4, right? So it's pushing a much bigger number into that sine function than the x value, right? Instead of 2, it's seeing 4. What about when x is 3? Now the sine function is seeing an input value of 9 instead of 3. When x is 4, by that time the sine function is seeing an input value of 16 instead of x equals 4. So the bigger x gets, the faster the input values start to increase, right? So does it make sense then that if I let b equal something like 2, that's what I'm getting, right? The negative values become positive for one thing, right? But notice that the further I get away, the more rapid the sine function starts to oscillate because the input values are growing as x squared, right? What if I make b a 3? Well, now it's growing even faster, right? You see what's going on there? Okay. This is kind of, and this hurts your brain a little bit first time you think about this stuff. But we're saying something here now where the input values are not linear anymore. The input of the sine function, we've got a function within a function here, composition of functions. The input values of sine are being given to us by a quadratic function, right? Okay, now, what if we do something crazy? What if we turn that around? What if we do something like the sine of 1 over x? Think about that behavior. As x gets bigger, what happens to 1 over x? Like start with x equals 1. 1 over 1 is 1. If x equals 2, I get 1/2. If x equals 3, I get 1/3. If x equals 100, I get 100th. If x equals 1,000,000, I get 1,000,000th. What value is 1 over x approaching? 0, right? As the number x gets bigger and bigger, 1 over x approaches 0, right? Crazy. Oh, are we done? Yeah, we're done. Shoot. Well, we'll pick this up tomorrow.